So it's my pleasure to introduce Professor Abhik Roychoudhury. I think we all know him and have seen his presentations before, and nonetheless, I should introduce him. He's Provost's Chair Professor at NUS, National University of Singapore, Computer Science Department. He's a world acknowledged expert in program repair, fuzzing. He has a rich body of work on that, and I've had the pleasure to collaborate with him on these topics as well. So he has won ICSE Most Influential Paper Award, 10-year Test of Time Award on program repair. So, and his doctoral students are placed in very good universities all around the world. He has served as chair of ICSE, FSE and such top conferences, and is currently chair of the steering committee of FSE, which is top software engineering conference. So it is a great pleasure and privilege to have him, and he's going to talk about program repair. So I think we'll get a ringside view of this area of program repair today. Thank you.
Thanks very much for taking the time this morning to listen to this topic, which is very close to my interests, which I call as trusted automated programming. So we started working on program repair. At that time, of course, there was no GPT or anything like that, but that was always with this view, at least in my mind, it was always with this view that the programming, how much of it can be automated, maybe at that time, one line at a time. And at the outset, I must tell Sujit that I will try not to get thirsty, but I left the bottle in the hotel. So in the worst case, I will take from this. But I will try my best to kind of give the whole hour without getting thirsty. Yeah. So I was listening to it with trepidation when you were. Yeah. Okay. Sorry? Yes, sure. I think that's very important, right? Because just like the notion of trust that I will talk about, when you can't achieve verification, you try to get trust. Similarly, sustainability, when you can't achieve, you at least keep the bottle far away. You give some. Right. So let's get started. So this will be the outline that we will talk about today. So I'll start about the auto-generated code, which is program repair, how we started on that field. Then the core problem. It's quite important to understand the underlying core technical problem, which is to uncover the programmer intent. And one way we are trying to uncover the programmer intent is through the use of symbolic program analysis. And then, of course, since then, there has been an explosion. Since the first works appeared a number of years back, there has been an explosion of works in this field. And gradually, the community is moving. It's always important to get the sense of the community. Gradually, the community is moving more and more into automatic programming. So to get a sense of where it is, well, in the community, we have been talking about this since 2017. So it's quite some time back that we should have a competition to really see where the community is going. But we didn't manage to do it so far. So this year, rather last year in 2023, from my group in NUS, finally I bit the bullet and talked to all the groups. And we just organized this first program repair competition so that we could get the agreement from all the groups working on this on what the format should be. And then, of course, my goal is to hand it over, but not keep on doing it. The first competition's results will be presented actually in ICSE in Lisbon this year. So I will not be able to tell you who were the winners and all, and probably that's not the most important thing as far as the technical aspects are concerned, but rather how we have compared the LLMs as well as the analytical approaches. So this is the first part, and then the second part, I'll probably shorten it a bit if we run out of time, because I understand we are probably running a little bit late, so I try to catch up on that. So essentially how we can do last mile repair of LLM generated code, at least I will try to give a little bit of a flavor, because that is also one way of engendering some amount of trust in at least how it can be integrated into code bases. The issue of acceptability of auto-generated code, this is something we have run a bunch of surveys, etc., at an extensive state. And also the role of these approaches in future education, because I understand there would be, in any software engineering conference, there would be quite a bit of interest in software engineering education. And also, if there is time, probably there won't be, how we can engender trust by extracting evidences from the auto-generated code, because this is also another way of engendering trust, that you get some evidence as a byproduct. Right, so let's get started. So this is the definition of program repair. It's very simple. You have a buggy program and you have some correctness criteria. Of course, to do repair, you have to have a notion of correctness criteria. And in program repair world, we always consider the correctness, or almost always consider the correctness criteria as tests, because that's what's most readily available. And we produce a patched program. This has many applications. So early on in the field, we used to look into things like increasing developer productivity, maintenance of legacy software, helping in debugging. It can help quite a bit in the debugging, because debugging is solving the mind reading problem. Like, for example, suppose I'm sick today, it's trying to find out how come I am sick, what happened, did I catch a cold, did I have a heart attack, and so on. Repair is trying to solve a simpler problem. As long as I can give this lecture, I can answer all your questions, I don't faint over here, you are okay, right? So that's the repair problem. So you really don't care whether I'm sick or not. So similarly is our is our attitude towards the programs. Think of it this way. And the underlying philosophy, whenever we are doing this research, even though all of the work is, you will see, probably very technical and a bit too technical, particularly in the first part. The underlying philosophy is always somewhat non-technical. That is, we try to see the program as a living thing which would heal itself, rather than seeing it as some lines of code about which some theorems will be written or tests will be generated. So this is the outlook we have always had, which is not the most technical, but I believe it helped in doing the technical work. So these were some of the earlier applications, but there are other applications like in education. I will touch briefly on that. There's also security patching. This is becoming increasingly important, and I'll talk a little bit about that. And also self-healing systems and drones. This is more in the more in critical sectors like defense. Okay, so let's get started. So the perspective is quite clear to all of us that we are having automatically generated code from tools like Copilot and ChatGPT and GPT-4 and so on. So what we would all want, okay, so this is really the holy grail of software engineering, that somehow you will write down things in natural language and out will come the code. So today you have that, except that you cannot really trust that code enough that you would kind of integrate it. Somebody once told me that you can really trust the code if you are ready to put it in your grandmother's car. So I wouldn't exactly say that. So certainly the code that is being generated from Copilot, would you put it in your grandmother's car? I'm not very sure. So this is what we will talk about. And one of the technologies in there can be the automated program repair. Okay. So this is the prospective, and also there is also the retrospective. So we wrote this article about 5 years back, or 4 or 5 years back. It took almost 2 years to write the article because we kind of tried to iterate over the whole community. This is the state of the community prior to GPT. So there are 3 main branches. That is the search-based repair, where you kind of automatically repair the program by just going over patch candidates. Okay, so suppose line number 70 is the line to be fixed. You generate all possible mutations of that line and you go over these patch candidates. And then the work that we have done, which I will talk about, is using symbolic execution. We actually call it semantic repair. And the main intuition or the main novelty over here is that instead of going over the patch candidates and asking this question, is this patch correct, is this correct, is this correct, you try to extract a property. Through symbolic analysis, you try to extract a property that all patch candidates should satisfy. And then you can use any number of techniques. It's just that since our group is a little bit formally inclined, we use program synthesis techniques, but you can also use backend. In the backend, you can also use search. You can also use, today you can use LLMs if you wish, with some properties being given as helps through the prompts. So it's really not that critical for us to decide on the engine which will generate the patch, but rather this viewpoint that you need to come up with properties or constraints before going on and searching. And along the way, there have also been learning-based approaches or inference approaches which try to work out some models of patches and predict patches. Initially, they started off by trying to help you rank the patches. For example, you have a semantic technique or a search-based technique, it will try to help you rank the patches. But nowadays, as you might imagine, LLMs can also be used to produce some patch candidates, the Gen AI, and I'll also talk about that, where it stands, so that we have a good sense. And just to give a sense, just so that it's not all abstract, just to give a sense of what is the kind of technical issue we are talking about, a very core problem is this so-called overfitting problem. Suppose you have a program with inputs and outputs as input 2, output 4, input 3, output 9, and you have a buggy program which returns input plus output, input plus input. Of course, the correction is that it should return the square of the input times input. So there is only an edit distance of 1. If you just change the plus to star, then it would become correct. But of course, if you have a terrible program repair engine, it might generate a repaired program like this. If input equal to 2, then return 4. If it equal to 3, then return 9, and so on. So you can always generate a very overfitting program, but that's not, of course, not the most interesting. And also, if you are not very careful about generating the search space properly, whichever way you generate the search space, whether by enumeration or by using some engines like LLM, that can be left out of this discussion. If you are not careful about generating the search space correctly, then you could end up with patches like this, these kind of candidates as well, like 1 greater than 0 and 1 greater than 0. You can have tautologies, you can have really completely unreadable things like this. Nobody would. So we want the patches or the code that is being generated to be really acceptable and somehow have a technical basis for that acceptability, other than just to decide it only by surveys. Okay. So these are some of the technical challenges. So the way we try to solve this issue is through specification inference, what we call a specification inference, where given the program, we will try to infer some specifications, but of course what we have is only the test cases, and this is the important thing. So you don't have a formal specification. If we have a formal specification, then many things will become easier. We don't have any formal specification beyond the test cases. So the main task is from these informal, if you agree with me that the tests are informal, then from these informal specifications, or rather the test cases, how you can extract formal specifications through the use of symbolic analysis and then synthesize patches from there. So this is really the viewpoint that we have. Another way, to put it another way for the more machine learning inclined among you, is that machine learning is always doing a generalization, right? Given some data points, it's trying to do a generalization. Here we are using a deductive engine to do that generalization, so to say. Okay. So let me give just one example. Everybody here has gone to maybe middle school, I assume, so everyone knows the triangle example. So I'll just give only this example and not all the very complex examples where you would need to follow through carefully. So here, this triangle example, it takes in 3 sides of the triangle and returns the type of the triangle. And there are actually many bugs in this few lines of code, not only the one I am pointing out. But this particular bug is that it has the definition of the isosceles triangle wrong. And I've written down a test suite, which I will not go through in the interest of time, which is exactly how a competent tester would write a test suite: 1 for an invalid triangle, 1 for an equilateral triangle, 3 for the 3 kinds of isosceles triangle, because 2 out of 3, and then 1 for a scalene triangle. This would be a minimal test suite that a competent person would write. And I'm just using this kind of a test suite so that it doesn't look contrived. And the correct fix over here is that 2 of the 3 sides are equal. So equal to B, or B equal to C, and C or C equal to A. So of course, you could try to traverse all the mutations, even if, for example, yesterday somebody came in my dreams and told me that, okay, line number 6 is the one to be fixed. Even then, you can traverse all the mutations of this. But if you traverse all the mutations, you will not be able to generate this fix, because this A equal to C, this does not appear anywhere in the program. So essentially, this ability to synthesize expressions that don't appear anywhere, that won't be present. So the approach that we took, I'll just mention it very briefly without discussing all of the technical details and without discussing the technique at all, is that instead of trying to kind of go over candidate fixes, we just try to generate some property of the fixes. So from these tests, which you agree that if they're informal, that we will try to generate formal specifications. So we can envision that this line, this is an unknown function of ABC, f of ABC, and then we will try to gain some properties about this unknown function f from the test executions. So in this case, 4 out of, I will not go through the excruciating pain of going through each of the 6 tests, but as it turns out, 4 out of these 6 tests reach this line, line number 6. So you will actually generate a constraint for each of these test executions. So for the first one, 2, 2, 3, it says that, okay, it should return true. So you get this constraint f of 2, 2, 3. And similarly for 2, 3, 2 and 3, 2, 2, and 2, 3, 4 should return false. And once you give this kind of a constraint to any kind of standard generating engine, including the program synthesis engines, if you kind of constrain the alphabet of what can appear, this would be a very natural fix to be generated. Okay, so this is just to give an idea. So at this point, as you see, we have not talked about the technique at all, underlying what is happening, but this is the kind of property that we want to generate without having to go through each of the candidate fixes, so to say. Right. So now discussing a little bit how we get these specifications from test cases, maybe just in a quick minute. So we show maybe one test execution and the way we use symbolic analysis. So we try to run this test execution concretely up to the line which we want to change. And at that line, we probably introduce, even though this is a second order actually variable, we introduce it as a first order variable, and then we do symbolic execution on that variable. Okay, so in this case, we will say that this is just x, and so if of x, and we will get some property about x, which will give me this constraint f of 2, 2, 3 true. So I will not spend too much time on the symbolic analysis, but there is a novelty in here, so which I will take 2 minutes to stress. So symbolic execution is a fairly well-known and fairly old technology. First appeared in 1976, so it's about as old as I am. And yeah, so I think symbolic execution, I think of it as my contemporary. So since I've spent so much time with symbolic execution, I think of him or her as my contemporary and friend. So symbolic execution, even in the first paper, if you look at it, you can see that program testing and program proving can be considered as extreme alternatives. So I'm very impressed with this paper 50 years later also, because in this paper, at the very first paper, the James King, he had said that symbolic execution is a generic technology which can be used for test generation as well as proving. Okay? So now, the way we are suggesting the use of symbolic execution for code generation, for automatic programming, is neither testing nor proving, but rather inference of specifications. So this is the only message or novelty I would like to quickly highlight. And you can see this again through this triangle example. There is no need to go through a lot of examples. You can see this just through this triangle example. The triangle example, you see what was symbolic here is this particular expression that I need to modify. Okay, so this is the symbolic variable. This is the unknown variable. Okay, so in symbolic execution, you execute the program in the presence of unknown variables. So instead of executing it with concrete variable values, you execute it with unknown variables. So what is symbolic here is this unknown variable, the patch that I will generate. Whereas when you use symbolic execution for testing or for program verification, the unknown variables are always the program input variables. Okay, so this is really the key difference. So here I will do concrete execution of the test, and then suddenly at some point of time, the line that I have decided to change, maybe based on some debugging, I will introduce a symbolic variable. And this is also why the technique becomes much more scalable, because for the test generation, you have to take all the input variables to be symbolic. Here, if I decide to change one line, I will have only one symbolic variable. If I decide to change 2 lines, there will be 2 symbolic variables and so on. Okay, so I'll probably not go into all of the technical details, but just highlight that this is being used for specification inference. And we do not assume, and this was very critical to us all along from the day one, that we will never assume the presence of any formal specification. So we don't want any formal specification, and yet we want to extract formal specifications by asking the question, what would make the program correct to the extent of passing these test cases? Yes, Raghavan. Yeah. Please interrupt me at any point of time. Raghavan. Yeah.
So one symbolic variable would be enough if that line of code will be reached only once.
But there will be many tests. That's the intuition.
A single test if it's in a loop, that line of
Right. In a single test, if it is in a loop, even then I will just have one symbolic variable, but I will probably accumulate additional constraints because it would not be an.
implicit may give a different value to that expression.
Yeah, but you would keep on accumulating some constraints on that variable because that variable, even though I am representing it as a first order, so this is the technical details I did not get into. Even though I am representing it as a first order variable for the purpose of my reasoning, that actually represents the value of a function with particular inputs. So you see the next time you visit that line, it could probably denote that function visited with other inputs, right? So this way you will keep on accumulating. I think you get the answer. Yeah. I can spend some more time on it. Yeah. So here you see you got 2, 2, 3. So you reached here with 2, 2, and 3. So A, B, and C were not mutated. Suppose this line was in a loop and A, B, and C were being destructively mutated. Then next time you need not come here with 2, 2, 3. So you will accumulate some, you will gain a little bit glimpse of that function, but for a different set of inputs. And in this way, in fact, even from one test, you can get a fairly rich specification. Yeah.
It's not a variable. It's not a single value.
Yeah, that's the entire observation, that we want to be in the first order domain, but be able to kind of simulate some amount of higher order reasoning, so to say. Yeah. Yeah, Deepak. Yeah.
That this should evaluate to true or?
No, not really. Yeah, that's a good question as well. As you can see here, I don't know because this is unknown, right? So I will do a symbol. So up to here was concrete execution. From here, I will start doing symbolic execution. So how I do the symbolic execution, there can be various strategies, but of course, many of the paths may be infeasible and so on. So from the paths that are feasible, you essentially answer the question, what it takes for this program to pass the test. So you think of the program as not a concrete program, but a program in this case with one hole inserted in it. So you are getting some property about what to fill into that hole and answering the question what it takes for that to pass just this test and just this test and just this test. And then if you had a fairly good test suite, which is often the case really when we care about the program, we have a fairly good test suite. Actually, you can generate fairly rich specifications without requiring any formal specification to start with. That's really the beauty of the whole method.
So I guess you know the path and the point that you should exit, for example, return isosceles.
I only know that it should return isosceles. So I know the oracle, right? Because the test is given to me.
But there could be many paths from there that take you to that point, if it's in a loop or something.
And then those paths could contribute to that constraint. In this case, there were only two paths, and one of them will steer the execution away from the desired value, and one of them only. So therefore, you get only one kind of constraint. Otherwise, all of those paths which let you rescue the execution, they would all contribute to the property. And then you can, of course, employ all of the research that has gone in symbolic execution to cut the explosion, etc., to keep it manageable. And there are many other things that can be done. I will mention them very briefly. So we have a fairly good optimization of this as well. Yeah. Yeah, I'll repeat the question. It's okay. So the question is that, is there any assumption on the program constructs that may appear? So this depends on the backend engine that you are using. So in the very initial works, we used a standard component-based synthesis. So there, of course, you have to kind of give some constraints about the components that can appear. But we, again, did not want to give too much constraints, right? Then you start. I want the programmer to be involved as less as possible in this because this is for automatic programming. So if you always keep the programmer involved, that is too much. So the way we got around that even in the very first cut is to do some sort of a layered search. That means initially you assume a very poor set of components and try to see if it synthesize, then make it slightly richer and slightly richer. This way, my aim always, at least the outlook, is to keep the programmer less involved rather than more involved. Yeah. But that was for a synthesis engine. If I have other kinds of engines, then the restrictions could be even lesser. Yeah. For example, if you use an LLM, you could, because from my viewpoint, it's only about generating the property. How you take care of that property, I really don't care. At this rate, I won't be able to go beyond the triangle example, but that's okay.
This looks like a comprehensive paper, but is there any criteria for like you want the branch coverage or?
No, I did. This is just for illustration. So there's this is
No particular requirement that the test can be.
the technique imposes no requirement. Given the test suite, it will try to generate the best possible property that it can.
It may not cover maybe just 10% of branches.
Yeah, so if the tests are of course poor, then you will be able to generalize less. This is for sure the test suite. That is given, right? So this is always best effort. This is exactly the difference between the trust and verification. Yeah, so we will not assume any property, even though in reality, always, of course, it will satisfy some coverage criteria. But as far as the technique is concerned, we will not assume any property about the test suite. But given the test suite that you give me, for example, for security, I can answer your question a bit more detailed. In security, sometimes we have only one test. Even then, we try to do a best effort. I will not have the time to get into that. Just from one test, which is the exploit, how we can generate patches.
I have one question here.
Oh, okay.
So ABC were concrete till that point, right? And they suddenly,
Of course.
after that statement, do they become symbolic, and then how?
Yeah, ABC does not become symbolic. This
Okay.
unknown function of ABC becomes
So
symbolic.
downstream, you still continue to evaluate with concrete values of ABC.
Yeah, of course. The only symbolic thing in here is this unknown function of ABC that
Okay.
I will insert. Yeah.
Okay.
So it's actually, so this is what I mentioned. I won't have the time for that, but this is essentially a second order variable. But I don't want to do that second order reasoning because that might be too costly. So I'm kind of representing it as if another variable, a first order variable, as if it appears in the program. Yeah. You can think of it as an auxiliary variable that I introduce. Yeah. Okay, so maybe we move past the triangle example. Yeah. Yeah. Right, but today I also want to share all the other advances. Yeah, very. Right. So this is so you could actually. We also later on, 5 years later, we also built a second order engine ourselves. We had to come up with a relatively quote unquote clever encoding because the encoding is quite important over there. To where directly, so instead of trying to represent this unknown function on the live variables through a first order variable, directly you have it as a second order variable, and then you have an engine which tries to solve not only the unknown first order variable but also this unknown second order variable, and then see the solutions of this second order variable are possible expressions. So then those expressions have to be represented in some sort of an encoding, maybe a tree encoding. So we came up with a tree encoding based on propositional logic, which is very, very fast, which can be used, so which definitely we will not be getting into. But as it turns out, just the takeaway from this is that for a second order engine, actually, irrespective of the number of paths that it's traversed, it's relatively stable. But in a first order engine, of course, because of the path explosion, it grows. But it starts from a low base. So this is something, and I feel this has not been studied yet. So if there's somebody in the audience who would like to take this up, definitely there is research opportunity. That means to come up with a second order reasoning engine, but specifically just for this problem, not a general purpose second order symbolic execution, but just for this problem of program repair. Certainly this is very open. We have not gotten around to it. Every time I just mention this and make a note for myself that I will look into it, but we have not so far. Yeah. But we wrote one paper in FSC 28 on this, 2018. Yeah. Okay, so 2018. Okay. So just to mention very briefly, there is one particular to answer this question about the path explosion, what would happen and so on. We looked into it for many years. And I will just mention one particular way this can be alleviated and leads to a very big wins that you can really scale it up to millions and millions and many millions of lines of code. And this was also done many years ago. So just to look into this by comparison with the search-based techniques, in the search-based schematic, you just go over a search space and validate each candidate against tests. But in the semantics-based schematic, you essentially generate a constraint for each test. And then what you have is the conjunction of these constraints from where you will synthesize. But whenever I say synthesize, you don't need to think about program synthesis. It can be some other engine also. Yeah, so you would synthesize. So one thing that can be done is, instead of representing this constraint, and I will not have the time to illustrate this with an example, but just the idea is, instead of representing this constraint explicitly and then working with these constraints which may become unmanageable, you can essentially try to represent this as sets of values. So that means instead of representing the constraint, you try to represent it as sets of solutions of that constraints and try to extract that value by solving this kind of formula. So instead of trying to capture one entire constraint telling you what it takes to pass this test, you can try to ask the question, if the rescued execution for this test was steered along this path, then what value it should have returned. If it was steered along this other path, what value it should have returned. So you can do some sampling over the paths, take a few of these paths, and in this way, of course, you don't have the entire constraint, but you have a set of values, and this whole thing becomes then immediately extremely scalable. But you are not representing the constraint with a single value. So we call these values as angelic values, that is, if God could not come on his own and then sent one of the angels to tell me what are the values which would somehow rescue the executions. But if that doesn't appeal to you, that's okay, we can call it something else. Okay. So these are some of the workflows we have looked into. I will not be able to discuss them in great details. So essentially, we have the workflow we presented is we have tests. From the tests, you do debugging, and then have dynamic symbolic execution and have program synthesis. We also looked into this possibility. This is something that can lead to maintainable code. You could ask the question that, well, given the test, can I look into the minimal disruption? If you think of the software program, just we get imaginative for a moment, think of the software program as if as a hardware circuit, and then as if what is the minimal change in wiring you need to do so that it passes these tests. You can ask this question. So then we can also have a max SMT kind of solver in the back end to answer the question that what is the smallest change in the program to make these tests pass. And then smallest change, then of course, as you might imagine, there can be many notions of smallest, the syntactically smallest, semantically which one would be the smallest change, and so on. So we did not look into this thoroughly. We only looked into the syntactically smallest because that's really what the programmer cares about. Okay. So my viewpoint is always that of the programmer. I don't want to get too much into the weeds of symbolic and lose contact with the programmer. Yeah. Yeah, it's okay. I can hear. Yeah. Yeah.
Development cycle, right? Where
Yes.
does automatic program repair fit in? Because we are expecting the location of the bug to be known.
No, we are
for
not
the-
expecting that.
No, but the line number 6 in the.
That's just for illustration. Of course, we have a fault localization step to show me the potential lines I will try to fix.
So we are.
And also this can happen in a loop. That was just for illustration, just to show the synthesis step. Yeah.
Okay, but fault localization is also an automatic. we are
Fault
expecting-
localization is also automatic. So in the earlier workflows, we use statistical fault localization, which is given a test suite, given a good enough test suite, it tries to assign a suspiciousness score to each of the lines. Later on, when we looked into other kinds of programs, kind of much bigger programs, I also saw it's a little bit better if you restrict the statistical fault localization not to each line of code, but probably lines that are connected by program dependencies. So then it works out a little bit better. So just for the sake of a quick answer, you could compute something like a restricted program slice and calculate the suspiciousness score of all the lines in that slice. Yeah.
Yeah. Thanks.
That generally works quite well. And also do note that the localization problem that you need here is not fault localization, but fixed localization. That means you say the fault is in line number 70. That is only in your mind as a developer because you have an understanding of the requirements and so on. It could be that instead of solving it in line number 70, it could be solved in line number 75 or 66. Okay. through different kinds of fixes. It could be that you have a 2-line fix, but the automatic technique will generate a 1-line fix. Yeah, so all of these are possible as well. Yeah. We are not being able to make much progress. Maybe we hold off a little bit if you don't mind. Yeah. Right. So let's reach at least the first half, and then we will take more questions. Yeah. So so these are some of the workflows we have looked into, like fixed localization, and then the dynamic symbolic execution and synthesis. Later on, we looked into this max SMT. And this max SMT solver-based approach for producing the minimal change, this was to me very useful, because even though this is not very scalable, this gave us the idea of how to get this concise semantic signature just using the values. This is how we represent, instead of representing them as constraints, we represent each constraint as a set of values, and this immediately becomes very scalable. These are some very old results, and since then things have come very far. I will present the results of the program repair competition probably briefly. So even in 2016, which is say 7-8 years ago, you can see already just by this idea of values, it's definitely able to reach a few million lines of code. And since, of course, things have come far. One other thing to mention is that the scalability problem in program repair or this kind of auto code generation is not necessarily about the size of the program, but it's about the size of the search space. So suppose you have a program which is only 50 lines, which is written by a first-year student in IIIT-B, say. Okay, maybe IIIT-B has very good students, so maybe some other institute where the student is not the best. And then repairing that may be very hard because the search space is very big. Maybe the student has made so much mistakes, so the edits that you have to consider is too much. It will completely change the program. Whereas repairing a 2 million lines of code written by a very competent programmer who might have just forgotten one check somewhere may be easier than that, solving the repair problem for a first-year student's programming assignment. So the scalability that we are talking of is not so much the traditional scalability of program size only, but also the scalability with respect to the search space. It's really both. Right. So, this is just for illustration, I guess, just to, today I'm giving the talk in the morning. Sometimes maybe I give the talk in the afternoon and people have had a heavy lunch, so I need to wake them up. So therefore, I have this heartbleed example over here for them to wake up, because everybody can relate to the heartbleed example. And you can see here the fix that is generated automatically. It's a little bit different, also coming back to your question. For example, here, this is the developer provided repair. The developer had a few lines. The developer is exiting when the payload is too big. And the repair that is generated is slightly different. It's just adding a conjunction that the payload should be small. So this kind of things we still accept as long as the patch is readable. Yeah, because it's really functionally equivalent to the developer, what the developer has provided. Okay. Right, so let me talk a little bit about the program repair competition. I won't be able to get into details because the results are supposed to be announced only in Lisbon in April. So we wanted to evaluate the retrospective plus this ... and the ... of course means LLMs, right? So which have now come in. So we did this first program repair competition. It's really a community building effort. We reach out to many groups, not just the groups that are participating, because there could be others who don't participate this time, but they will participate in the future. So what's a fair way of comparing? So we had these tracks over here: functionality errors, student assignments, as well as codex errors. So we also had one track on the codex errors. That means the code is automatically generated and then how you fix them. We also didn't want, because there is a lot of effort, not just for us to run the competition, but also those who participate in such a competition. And it's not necessary that it will lead for them to be a paper or something. So we want to encourage the students and everyone to participate. So what we did is we took the benchmarks which have been traditionally used as much as possible, but we use different bugs. So we don't want the techniques to be overfitted, okay? But we also don't want people to spend a lot of time just building something which they are not very familiar with, this, that, etc. So we generated lots of new kinds of bugs to kind of test out the different repair tools. So these are some of the participants who participated from majority of them from US and China, one from UK and one from Sweden. There were also other participants who in fact dropped out, who said that the standards we have set is too high. So this is also something to think that there's always a delicate balance when you try to move the technology forward, that you want enough participation, but also you would like to kind of move ahead. There were 10 tools which participated in the end. Of course, a lot more people. There were 475 repair tasks and so on. So this is just to give a little bit idea about the evaluation. So given the repair tool and the track, we have this so-called Cerberus platform, which slaps together as many of the repair tools of the world as possible, so to say. And anytime anybody wants to enter a new tool, it's just slapped into this platform. So this is the way we can run the competition more easily. And there is a configuration and execution process, of course, and then we only take the top 5 patches. And of course, there is a public test suite and a private test suite. We, of course, have to have a held out test suite. And in fact, there is also an adversarial test suite. So this is the kind of validation that we did. We considered the execution results as well as the resource usage and the time latency. So you might be interested in this categorization. This is the way where it could not even build, incorrect fixes, which means that it failed the public tests, overfitting patches, which means that it failed the private tests but passed the public tests, correct patches, which means that it passed the public tests and the private tests but failed the adversarial tests, and finally high quality patches, which means it passes the public tests, the private tests, and also the adversarial tests. So this is the way. Now, exactly how you do the scoring, as you might imagine, exactly how much point you will give, etc. There are many possibilities here, which may not be very interesting in a technical talk. And we also consider the score from these patches, the latency, as well as the usage. Okay. So yeah.
So I was just wondering, this is about this competition as well as all the body of work that you mentioned.
Yeah, and this is also too because we also wanted to see, this is, if I get time, depending on how much time there is, I'll also mention this later. We also wanted to see whether LLMs can really take over this repair task, right? So that is something to benchmark. Otherwise, why should we put in more effort in doing research on program repair in future? Suppose the code is also generated by LLM, then it is repaired also by LLM, and it works out already pretty well. Then why should we do? So that's also part of the message from this competition, because we wanted it to be very clear and transparent to the entire community that actually the repair task cannot be done by LLM. Yeah.
So my question is, the evaluation parameters, would you not like to include something like user acceptance parameters? For example, at the end of the whole story, even if the test cases pass, if the programmer doesn't find that code to be appropriate to the situation.
So I think that's a fair point. So Sujit's question is that why don't we consider also user acceptance parameters? The answer is we didn't. In this first competition, we didn't. You can see already some teams dropped out, right? So we also want the competition to have enough participation so that the community can move forward and improve the technology. But this is something we have in mind for the second competition or so. One thing that I can mention is even this slightly nuanced notion of correctness. Many of the tools, including specifically the LLM tools, are not able to satisfy. So this is the main, some of the main messages. So the fixed localization, it's still a challenge. There is a lot of bit rot in these tools. So that means somebody, and this is what I call as a PhD tool. Or for all the PhD students here, probably you know what is a PhD tool. After your PhD, nobody can use your tool. Yeah, you run away with your PhD, and so please don't build PhD tools. So there is a lot of bit rot, and this is something we found. But one of the good things about this kind of a competition is that you see when a tool is participating, it's not necessary that the original author of that tool is participating. Somebody else can also take that tool and participate. So in fact, since I'm running the competition, I didn't participate. But as I saw, one of the teams, they actually took one of my tools and they kind of made it their own, and they decided to participate. So that is also useful because people then know all the challenges of using the other tools rather than just writing some academic papers and then nobody else ever following it up. Yeah. So the impact of bitrot is quite high. This is one thing for the LLMers in the audience. So we saw that if we look at the various LLM tools which participated, some of the fine-tuned LLMs, specifically using this Code Llama and Star Coder, they actually outperform GPT-4. So some of the participants, they put a lot of time in fine-tuning, probably in they did a little bit of training. They provided the training data in some novel ways and so on. So there is certainly some room over there. And then the validation, this is something we saw. When you produce the patches, what is a good quality patch? What are the right tests to look into? This is still being overlooked by the research community because, of course, we want to write our papers very, very fast. So this is something we would want. One interesting thing, at least to me, is that whether the LLM-based repair actually generated a lot more patches, but most of the time they were incorrect. So there is certainly more ground to cover. Yeah.
Did you find any correlation for the specific kinds of tasks LLM perform better?
I'm sorry, but it's not in the interest of time, but because the results will be announced in Lisbon, so I'll not be able to disclose this any further. Yeah, but this is not in the interest of time. Yeah. Even this one, these slides also, I carefully checked through whether I'm disclosing anything that I shouldn't. Yeah, but this is fine. Yeah. So I'll cover the remaining things very quickly, maybe. So of course, language model-based code generation, everyone here is very familiar with. There are so many of these tools, Alpha Code Whisperer, Codex, and so on. So one of the things that we looked into is that we created a new data set because we don't want this to suffer from data pollution, something that, say, the generative AI tool has already been trained on. So we created a new data set from certain lead code tasks which were given out later beyond the time period that it was trained on. And we generated 5 codex-generated solutions for each task. So I'll not get into the details of all of these results in the interest of time, but one interesting thing that I can highlight for the purpose of research is that we saw that there are 1/3 of the errors are so-called misaligned algorithm. You know what is a misaligned algorithm? That means given the natural language specification, it's the generative AI tool is trying to divide that task into various subtasks, and then for the subtasks, it's trying to come up with some code which solves that subtask based on whatever it has memorized. So misaligned algorithm is essentially a very euphemistic way of saying that it got it all wrong for one subtask. Okay, so probably it copied a different algorithm. Even the algorithm is wrong. So which really means that there is from the research point of view, because if we really look at it as how we move this technology, from the research point of view, this means there is a significant amount of ground to cover. Because these kind of things like the syntax error, 47%, I'm sure maybe in the next release it will become 37% and then 27% and so on. So there's really no point looking into that. Right, so we also looked into some of the syntax-based repair tools, specifically the pattern-based repair tools. Can we use them directly on this auto-generated code? We also tried to use the auto-generated coder on the code generated from the auto-generated coder. Okay, so therefore, the tools that we used here, this is a pattern-based repair tool, T-bar. We also used the codex edit mode, which at that time was available, and now it has been discontinued. So the codex, this is to really answer the question whether we can have LLM generate the code and LLM also improve the code. Basically, it's just LLM and all. And so one of the things we found is that is not the case. And just in case we want to have a complete discussion on what we tried out, these are the kind of prompts we gave. We could just say, go fix this bug. Okay, even that is possible. Then it will essentially try to modify each line and just make an attempt. You can give the line number, but in this case, we are giving the line number, trying to help the LLM. And since these are natural language-based tools, giving the line number and giving the statement for that line number, that actually makes a difference in the efficiency. So that's quite, at least to me, that's quite interesting. So these are again some of the takeaways, that many of the tools have improved quite a bit, but they are subject to a good localization. So one of the benefit of this kind of an LLM prompt is that you have a more flexible fault location. You just say fix this bug, and you don't try to indicate the line number at all. That's useful. And another thing, and this is also quite instructive, at least for me, is that it's useful to look into the semantic analysis-based repair tools, particularly when the code is being generated from LLM, rather than the pattern-based ones, because whatever pattern you might enumerate in your pattern-based repair tool, the LLM has, of course, seen it all. So, so there's really no need to have that. And this is, again, something from the research point of view, I think that's quite interesting. Yeah. And also, these were done with Codex edit mode. Of course, since then, there are many other things, GPT-4 and so on. And we saw that really merely changing the LLM doesn't work. So again, there were lots of results on that, and I wouldn't want to take up your time. So moving on, this is just one slide to sketch something which is a little bit futuristic maybe. Moving on, there might be opportunity. There's, of course, a lot of opportunity, but there might be opportunity in linking up the programs, because the LLMs typically generate not one program, but multiple programs. There might be opportunity in linking up the programs with the natural language specification. So whatever we solve in software engineering, we often call it traceability, right? So there might be opportunity in trying to find out which parts of the natural language specification are not being satisfied by which of the programs, and trying to find out the reasons. This is one direction we have started working on. And this way, the edits or the mutations of this program, they can be guided. So we really call them a bit more semantic mutations. They can be guided by these parts of the specification which are misaligned. And that's how we are trying to guide the mutations at this point of time. And this seems to produce, again, fairly good results, but it remains to be seen. We have very little time, so I'll just briefly mention, we looked into the use of these technologies and also the role these technologies can play in education, partly because, of course, also that I'm myself in a university, but also the presence of these technologies would change the education sector significantly. So one thing that we did to generate a very high degree of realism, because we really want the thing to be very realistic. So I created this new course in our curriculum structure. It's called Foundations of Software Engineering, so FSC. The name of the course is FSC. So what we do in that course, apart from teaching the foundations, is that we kind of build an intelligent tutoring system. But we teach this software engineering of this intelligent tutoring system not in the conventional way, but in the way you would teach an operating systems course. In an operating systems course, you will have a base operating system, and the students will go and add some features and make it a full functional operating system. Similarly, I will give them every year an intelligent tutoring system. Initially, in year 0, it does very little, but all the stubs, all the templates are in. At the end of year 1, it is a little bit functional, and it will be given to the first year students for while they learn programming, and they will give feedback. Based on that, the year 2 projects will be generated. It will become a more intelligent tutoring. So over 4 or 5 years, it will become much more intelligent. And then by that time, the students in the 0th year, they have left the university, and you can roll back if you want, or you can keep on making it more and more intelligent, either way, whichever way you want to do it. Yeah. So this is something we have created, and this is also one good way of trying to find out whether because in my mind, apart from solving these millions and millions of lines of code written by a very competent programmer and repairing it, this is also a very hard problem. That very bad code written by a first-year student, how much it can repair, what kind of feedback it can give, what kind of grade it can give. We are also looking into doing the grading automated. And also, of course, there is a lot of need for it, as you might imagine, because right now at NUS School of Computing, we have 1,700 students entering to learn computer science. So, of course, it's a lot of work also to do the grading. So, leaving aside that practical value, there is also some lesson to be learned. So this is just a little bit of details about the structure. So this tutoring system has a parser, then alignment, error localizer, repair, feedback, auto grading, concretization and so on. So the students will do a project just typically in one of the modules. They will improve one of the modules. And this works very well because the main reward of the students is that there is no prize. The main reward of the students is that their code will be accepted to go into the code base. And this they find very rewarding because then immediately their juniors will start using that code and giving feedback about how the tutoring went. So one interesting thing in here, so we learned, of course, a lot of lessons on this. And in fact, this year in Lisbon, in the ICSI education track, we are also presenting this experience in a paper. But we learned many lessons from this. But one interesting thing, which in fact we are doing the pilot study right now, this semester, as we speak, it seems we can also use this kind of a system in future for teaching algorithms and data structures. So we are actually right now doing a pilot study for a second year, not a first year programming course that we have already done, for a second year algorithms and data structure course, where this repair that is generated at a low level, at the programming level by our tutoring engine, gets aided by LLM to provide the feedback to the student at the data structure level. Because whatever you teach in the data structure course, the LLM, of course, has a lot of understanding of it. So this is something also, I don't work in intelligent tutoring, but I reached out to many colleagues who work in it, and they thought that, okay, this is something that has not been tried, and this might be interesting. So I'm still exploring this, and I would be very interested to talk to anybody who would be looking into this space. Okay. Yes, we should finish up, yeah. I'll just mention that it's very, very important for the code to be acceptable, and we will not have the time for that. But we ran a number of studies, and this is just one study. It appeared in ICSI a few years ago. You can see about 100 plus people like developers, architects, QA engineers, tech leads, and so on. It gave a lot of comments, which is very important, I think, for while writing a research paper. It's very important to look into. Because oftentimes you generate lots of patches, but then the developer is not going to look into so many patches. You take a lot of time to generate them. One very interesting outcome from this is that there is an expectation from developers and architects that the repair technique should generate test cases as evidence that it is correct. So this is something to think about. So let me just make a few quick comments about evidence. We are looking into this kind of evidence. That means you have specification from natural language, auto-generated code, test suite guiding the repair, but then the repair, apart from the code, is also generating some evidence in the form of additional test cases. And the way we look at it is in this video, as you can see, there is a space of candidate patches. It is constantly getting shrunk as you cover the space of inputs more and more. That means cover more and more paths in the program, say. Okay? So this is one way also of generating evidence that we are looking into. These are some of the things on security patching that we have done. So Raghavan mentioned we should wrap up. So I think moving ahead, there will be this question on when the ML generated code can be trusted enough to be integrated, and therefore there will be this need of the repair technique itself generating evidence. So this is where we started with many years ago, program repair on manually written code, and moving forward, this is how we have sort of pivoted ourselves while still maintaining the same techniques, that the specification is in natural language, auto-generated code, the test suite is there, and then apart from the code, you also generate additional test cases in the form of evidence. And in fact, this evidence generation is turning out to be very critical for the security repair, security patching. I would like to thank my students. There are many of them, but these three of them, they are now faculty members in actually 3 different continents. Gao Xiang, who is in China, Xin Hui is in Canada, and Sergey is in UK. So they are all in 3 different continents now, but of course I keep on having touch with them. And one distinguishing feature of all of them is that they took a lot of risks in their journey, and they contributed to this imagination rather than only trying to come up with newer and newer techniques. They could also contribute more to the viewpoints, and I think that was the most rewarding. And I will also like to acknowledge this program. We are running this program, so we have enough resources to run this program repair competition and get started. So I would like to thank Ministry of Education, this Tier 3, for giving us the opportunity for this program. And we have done this community involvement for the repair competition, but there is also more community involvement to be done, and there's this Darkstuhl seminar later this year and a Shonan meeting in January next year, and with my co-organizers, whom also I would like to acknowledge. So with that, thanks very much.
So I would also like to mention that Abhik accepted our request to come here, our invitation at a very, very short notice, which is very difficult for him. We know that he has a very busy schedule. In fact, he's flying out very shortly after this. So, I would say that shows his generosity, and we must thank him for that too. So thank you, Abhik.